Welcome to Modular March. I'm Andy, this is Robbie, and we are The Roll-Up.
Modular March is an educational experience about all things modular. Enjoy.
Welcome back to Modular March. Today we have Karel from Union Build talking about the sovereign interoperability layer. Welcome to Modular March.
Hey Andy, super excited to be here. I'm going to talk about Union, the sovereign interoperability layer for the modular stack today, as well as some more philosophical mind share about modular versus monolithic and kind of the utopian abundant future that we're all trying to build.
Fantastic. Looking forward to it. Of course, Rob's here, and not our first presentation with Karel, but I feel like this is going to be the most interesting one yet. So excited to dive in. Let's do it.
All right. So for a little bit about me, I'm Karel, 0xKaiserKarel on Twitter, so give me a follow. I'm a developer, meaning crypto since 2016, doing anything from Solidity, Substrate, Cosmos, SDK, basically all across the stack, and founder of Union Labs, currently heading that. Today, I'm going to be chatting a bit about my modular mindset and how I see kind of Web3 as a whole transitioning from a monolithic stack where a lot of control lies in the underlying L1 to far more abundant stack where I, as a developer, can actually finally build what I want to build. To start discussing that, I first want to kind of dive back into originally why Ethereum and almost why crypto. Web3 is the goal of building the world computer. Basically, one layer where any DeFi computation can happen, where code is law. So when you interact with an app, a protocol, it's completely predictable what's going to happen, completely trustless, no intermediaries, no company that could dive into the database and alter your funds, for example. Verifiable. So not only do I know that they're not capable of doing this, but I can also check that they're not doing this and track this. And without any intermediaries. In general, the only layer that we have is the mining layer or the validator layer. And no other off-chain component can have any control on the contract. That's really the goal of Web3, of Ethereum, of Solana, and really, from a dev perspective, what we're trying to build. What this results into, of course, is a really great use case for finance, because in the end, finance is kind of the frontier of, I would almost say, combat right now. Like we do economic warfare, restrictions. This is where kind of most of the cowboy land is right now. And so having all of these properties in finance is the clear use case for Web3 to me. I think with DeFi right now, 100% what we see. Where we're kind of see this power come from is the composability. So the reason why Ethereum is so great is I write a really simple contract, someone else writes a really simple contract, and someone else can build a third product by combining these two. We have this money Lego concept where basically with just a few core products, we can create almost infinite products, like a real Cambrian explosion of products, all because they are composable. Composability only works when the protocol interactions are the same security level as just calling a single contract. So if I call a contract that does a swap on Uniswap, that has the same security guarantee as if I interact with some vault strategy that interacts with Uniswap. Like that interaction between the DEX and the vault contract has that same security guarantee, and that's why you can do this composability. For me, at least at the moment, we're building one single global computer. That's what we see with Solana. That's what we see with Ethereum. And this kind of, at some point, leads to a bit of a dystopian future, because the single computer, first of all, cannot scale. So we have issues with MEV, and only high-value transactions can get in. So not everyone can be included anymore. And there's an issue with censorship resistance, because one single global computer has one single global sequencer in the end. And so what we might see, for example, is validators unwilling to include transactions for Tornado Cash, or perhaps for certain country IPs at some point even. And so building towards a singular global computer leads to a world where we're not really Web3 anymore. We're not really doing open finance for everyone. to me, the solution to this is modular architecture. This allows us to scale infinitely, while at the same time remaining censorship resistant, having products for everyone out there. In the modular stack, we have a few concepts to kind of have the same guarantees of composability. So obviously shared security, which allows us to create many different blockchains, but still have the same massive security that Ethereum has, for example. Other execution proofs, even the next generation of this, it basically makes it so you almost don't need shared security anymore, because now you have mathematical indisputable correctness. And then, of course, we have data availability and sequencing, which kind of separates this into individual stacks. And that allows us to basically offload certain risks, because now the parties that are responsible for execution don't decide on the order of the transaction. So you get more censorship resistance. And modular is obviously on the rise. I don't need to tell you guys that, but over the last couple of years, we've seen this Cambrian explosion happening, and it's only continuing like this. So to me, this is amazing to see. This is the vision why I originally went into crypto, to really kind of see the full wideness of experimentation. However, there are still a few problems with modular. The way it's right now is it fundamentally cannot succeed. It cannot beat Ethereum or Solana yet. Because what we gain in security and censorship resistance at the moment, we lose in composability. Asynchronous composability, basically bridging transactions and other interop, at the moment just isn't as good as synchronous composability. We don't yet have those same guarantees that you get when a vault contract calls Uniswap. We don't have that when an L2 calls another L2. Really, the issue that we have right now is that we do go outside of this very pure mathematical blockchain space, and we kind of add this third-party intermediary to facilitate composability. And obviously, that's not going to work out, because the world of interop that we live in right now is kind of the same as if the Ethereum Foundation would need to whitelist every single contract. Can you imagine that? Like if they had to do that since 2015, we wouldn't see this Cambrian explosion. We would have 60 contracts on Ethereum right now and nothing would be going on and no experimentation could happen. And that's kind of the main limitation factor right now with composability, with interop, is that we don't have yet the kind of same guarantees, the same security that allows us to allow this composability. Synchronous, we have code is law, we have atomic execution, and it's really kind of Web3 ethos. Asynchronous, we have these intermediaries. Sometimes they are oracles, sometimes they are multi-sig contracts, sometimes they're market makers with intents, but they still don't provide the same guarantees. We don't have atomic execution, so we end up with these like broken states, funds are in limbo, and especially if you do like contract-to-contract calls on different layers, you can't have something remain in limbo because contracts can't like make an API call, dive into a database and such. And so then you need all this off-chain architecture to fix up these limbo states. And then all of a sudden, it's no longer a pure smart contract or pure protocol. It's a whole Web2 service that you need to run next to it to keep it working. And most of the time, to fix these broken states, you kind of need to use like admin keys or some form or another to deal with this. So the real question that we at Union ask ourselves and that we try to build for is, how do we make asynchronous as good as synchronous? Like, how do we introduce the same guarantees that we get in monolithic stacks into the modular stacks? And that really is the solution to making sure that modular succeeds in the end and that we can build out this abundant ecosystem. It's also some of the hardest solutions out there. No longer do you just get the ERC20 interface or ERC interface between smart contracts. You really now need to dive so deep into the security stack. And that's part of the reason why we haven't seen these products out there yet. They're just a lot harder to build and they require a ton of research to do so. So in the space right now, a few shortcuts have been made by different interop providers. That's fine, because in the end, like we need to get product to markets and we first need to deal with the world of like 30 chains wanting to talk with each other. But in the end, with modular, we're working towards a future where we want 10,000 chains and 10,000 rollups to talk with each other, even 100,000. And right now, intro protocols deal with 80 to 100. So we're really just not there yet at all. What we really need to do to support this future of like 10,000 chains or 100,000 rollups is invert control. Just like the Ethereum Foundation can't whitelist all of the contracts, an intro protocol can't have a BDQ and just talk with teams and decide we're going to do this one first, this one next, because then it's just never going to scale out. Then we remain in this kind of Web2 mindset of permissioned systems. Really, this should be interoperability. Interoperability is not a privilege. It's a right? Any builder should be able to create an app chain, create an L2, and connect to the wider ecosystem. That's not something that's only reserved for projects with already billions in TVL that are extremely hyped. Like, I love protocols like DYDX, Parachain, and such, and they have no issues doing partnerships with major intro providers. The question that we need to ask us is, how can we make the next 10,000 or 100,000 startups build the same products or competing products or new products using those same stacks? Startups that don't yet have 500 million in funding, don't have a massive community, but instead are starting from scratch. How do we provide them unstoppable systems as well? And how do we get them to hyperscale? So for that, interop needs to be inverted. These startups need to be able to integrate themselves. They need to be able to just boot up their new layer, connect to the intro protocol, and permissionlessly connect. To do this, obviously, it needs to be extremely secure and trustless, because if you're going to allow others to connect to you, now you introduce potential vulnerabilities, right? You can't just trust any chain. You can't just have them run a multi-sig bridge and blindly trust that multi-sig bridge. Because the first thing I would do as a dev is set one up and just like min sense with my multi-sig, right? So really, we need to rethink the underlying security systems that we have for interop as well. And to us, at least, like, security is not pick and choose. Like, we see some protocols out there that say, choose your own security, do like multi-sig for certain messages, do fraud proofs for other messages. That just leads to a massively complex interop layer, and one that leads to a lot of vulnerabilities. Like, do you really want to make all of these startups think about which message needs to be of the highest security, which one doesn't? Or does it lead into situations like Tornado Cache, where the fundamental protocol was secure, but the DAO that governed it wasn't monitored as much, and someone just manages to sneak in a proposal? If you have the same with these messages being sent out, maybe this new protocol decides a security standard for a message that's too low, which an attacker uses to, in the end, hijack the entire protocol. Just like with websites, right? Like, we have HTTPS everywhere now. It's just not a trust. Like, it's not only for banks. It's not only for financial transactions. Everything should be just at the highest security level for this to work. So otherwise you lose the composability again. Imagine a world where some smart contract calls on Ethereum are trustless and are pure, but other smart contract calls are not at all and might just go through a hackable intermediary, but it's not observable to you. Now, as a developer, you can't just integrate any contract anymore with the same security guarantee. You need to dive into every single one and assess what's going to happen and have a home security model to it. Really, to achieve kind of the same guarantees that we want, you have to do consensus verification. That really is the only possible solution that scales to what we want to build with interop here. Consensus verification inherits the same security guarantees of the underlying L1s that you're bridging. So in the end, you inherit Ethereum security guarantees, Celestias, and you don't introduce third-party intermediaries. And that's kind of the best that you can do, right? Really inherit the billions of security underlying. And really, the only way to do consensus verification properly is using zero-knowledge proofs. This, for the less technical people here, really is a scalability thing. If we go to this abundant future of 10,000 rollups all integrating with each other, we can be allocating 50% of our block space to interop. We can be filling everything up with bridging transfers, because in the end, we want user transactions. We want swaps, we want LPing, we want gaming, etc. And we want to make this communication between apps as like little cost as possible. And with ZKPs, you get that scalability. You really ensure that you basically have a constant cost. You allocate 0.1% of a block to interop, and you can connect to as many chains as you want. And so this leads to this hyperscaling, this high security, and really makes asynchronous composability as good as synchronous. And then permissionless infra is what leads to hyperscaling. There's tons of dApps out there, trust me, that want to build their own app chains, their own L2s, and have full control of the stack. But really, right now, there's just some fundamental business choices that don't allow them to do this yet. Making interoperability right is really what allows them to do so. If, in the end, the interop protocol has to choose to support different chains and has to make value choices there and make a stance, it will fail in the end. It cannot scale with crypto. It cannot scale with Web3. It then kind of becomes its own like permissioned corner that, in the end, at least to me, isn't aligned with why I originally started developing on Ethereum, which was to be sovereign, to have full control of my funds, to build whatever I want, to do with it what I want. We at Union have chosen to use IBC as this core protocol. IBC is originally from the Cosmos ecosystem to connect app chains. It's kind of really the TCP of Web3, fully designed to adhere to everything I've said so far. We also made the decision not to do our own proprietary protocol because there are a lot of intro protocols out there right now. And in the end, that means that instead of having 14 competing standards, you have 15 competing standards. So we made the choice to instead align with what we thought was the best standard. Meanwhile, IBC has grown a lot. When we first started building on it, it was about 200 million in monthly volume. Right now, it's about 4 billion in monthly volume. I think out of like all intro protocols, it's number one at the moment in monthly volume. And so really the rise of grassroots protocols that kind of originate from the developer community to really like solve this core need. I think it's going to be a leading narrative in kind of the next modular wave. We saw with like the rise of the internet that a lot of massive companies that were kind of too big to fail tried to do their own proprietary protocols. IBM had their own version of internet protocols, and Bell Labs working on it. But in the end, like none of those really succeeded. And what kind of succeeded were the devs with the gray beards in their attics working on Linux, inventing kind of protocols that didn't have any like kind of PC backing, etc., that reached the top. And so that's our bet as well. What are we doing right now? So Union itself connects basically IBC-enabled chains. We do IBC integrations. We connect with different settlement layers, with different data availability layers. We support sovereign rollups and rollups building on the sovereign ecosystems, for example, movement. Right now, this doesn't yet show Avail, but some alpha, we are working on Avail integrations as well. And then finally, basically integrating the kind of more pure EVM rollups as well that don't just sadly like arose in the Celestia ecosystem or the Cosmos ecosystem as well. Really, the objective is to have that one standard interop layer across everything that just supports whatever developers need to do. And this is kind of our objective for the next year and a half, but really the big picture, right? And the like utopian future that we're working towards is proof of proof technology. First, we get to a world where chains are sending hundreds of ZK proofs to each other, all with their individual channels, different connections, and a routing layer that's necessary. But the future of ZKPs is actually collecting all of these proofs and then putting them into one single ZKP, which you then send out to all the chains. This leads to that massive scalability where you only need to allocate 0.1% of block space to interop, and you literally have a connection to every single chain out there, not 100, not 1,000, but 10,000. This is also where I think the frontier of intents is going to happen. Because if you have this like fully trustless layer based on ZKPs, it's incredibly cheap to run. You basically build a decentralized sequencer for interop, where every single blockchain that you're connected to is kind of a mempool that goes into this decentralized sequencer, where you could do intents, coincident of ones, do all of this inside that ZKP, settle the ZKP everywhere. And so you're not even paying gas for these intents. You're not paying gas for these coincident of ones. It's literally the same gas that you're paying for the security itself. And now that's kind of the modular utopian future that like we're building towards, that I want to see, that basically can just completely subvert Web 2, TradFi, and which we can use to reach trillions in volume and basically like get everyone basically banked, or at least crypto banked. That's my objective, that's Union's objective, and that's at least why I'm excited about modular and what my modular mindset is. Horizontal scalability is the future. I think everyone in this call fully agrees on that. Lightlines and ZKPs are what can support this or enable this. And really, the future is modular. All right, guys, that's it.
Yeah, that was awesome. Ton of questions. Going to start all the way back and then dive into some of the stuff in the beginning, or sorry, more towards the end. I wanted to particularly touch on this one. On this, could you maybe just unpack this decentralization spectrum a little bit and walk us through maybe some brief technical overview of each of these components and how they kind of stack up against each other, going from centralized all the way to decentralized?
Yeah, exactly. We can kind of divide this into two halves. On the one half, we have the single signature, multi-signature, and MPC quadrant. These are all technologies that rely on having a set of off-chain actors that we trust. Really, they're kind of security optimizations. With a single signature system, you trust a single signature relayer. I'm not sure if we saw many intro protocols do this. I'm sure there's a few out there. I think Kava actually right now relies on this. This is obviously like extremely risky because you have a server somewhere doing bridging transactions with a single private key, and if hackers get access to this, it's dumb. From kind of a bigger picture perspective, it's also a bad idea because you fundamentally trust a single party for your protocol. So even if this party isn't hacked, if they receive a letter from the SEC or the NSA knocks on their door, or they just decide they don't want to comply anymore, then your whole system falls apart. As a security optimization to a single signature system, you can do multi-sigs. There you basically pick a few parties. So you see 3, 5, 7 parties that need to collaborate and collaboratively sign. A downside is you kind of usually see that these are parties that know each other, right? Like 2 are devs from the protocol, 1 is an investor, 1 is an infrastructure provider that's a seed investor as well, and 1 is perhaps some other person that they knew. And now you have a decentralized system, but really it's still 5 people running a server in the US that still have that same vulnerability to the SEC, the NSA, or just deciding to collaborate and break the protocol. Multi-party computation can kind of scale multi-sig out to 100 nodes. That's what XLR uses. If you combine that with like a validator set with token governance, you do have like a much better system and a much more secure system. But in the end, like validators know each other, or you still have like a group of off-chain parties that make decisions for the protocol. And so bigger picture is still not that great. Then we go into the actual decentralized corner, consensus verification and state verification. With consensus verification, we inherit the security of the underlying validators of the 2 chains themselves. So we don't introduce like a new group or an off-chain party that has to make these decisions. So that's kind of the best you can do, because you already rely on these validators because they are the ones running the different chains. So you don't add any additional security assumptions. What you do have with consensus verification is if 2/3 of the validators are malicious, which, to be honest, I think has never happened yet. And it's really hard to perform an attack like that. But you do have a risk if that occurs. State verification is like the full golden standard. And basically what you then do is you combine the validators as a settlement layer, but the state transition, so the execution is the ZK rollup itself. And that way they cannot commit fraud even if they want to do this. That's kind of the golden standard. That's what Polygon is working on with their aggregation layer. The downside is right now, you can't do this for any chain. You can only do this if you like support very specific ZK rollups, which are quite limited in their capabilities. And so if you want to support like the Cambrian explosion of products, then at the moment, this won't work yet. For example, skip protocol Slinky wouldn't work at the moment with this. So you're really like limited with what you can build. That's why I think kind of the sweet spot at the moment lies at consensus verification until we make a little bit more progress with ZKP technology. Right now, for example, even close to things SP1 is great. If you want to like prove a full Ethereum block, it's still 40 minutes to do so. Until we get that down to 12 seconds, really state verification is a bit too far away to be usable for the ecosystem. I give it about 3 to 4 years until we get there, maybe earlier.
Awesome. Great. Yeah, Rob, you go ahead.
Yeah, I mean, what's the limiting factor? Like, what are the obstacles? What are the blockers for state verify? Is it a hardware? Like we just don't have the processing power, or is it more of a mathematical problem that we're still trying to solve?
No, it's really about processing power. So right now we can do it. It just takes way too long. So things like GPU acceleration, ZK ASICs and such can basically unlock this. Hardware has a long cycle, right? Like you can't iterate on a weekly basis. You have to build these chips, iterate again and again and again. So we see right now performance from ZK ASICs is good enough. We just need a few iteration cycles to actually get there.
Gotcha. Another really interesting point was, this might be simpler than I'm trying to make it. On these 2 slides, you mentioned in this feature with one proof to rule them all, you've got all these different chains interacting with one, ZK proof that is basically able to be shared with all those chains at the same time simultaneously with a very small percentage of a given block. I guess just like, how would that look? So in a block, there's different sections that are made of like the state of the transactions of like, which validator validated the block. And then there's like, I guess just talk to us a bit about how these blocks are like structured, like what the subsets are and like how.
When I talk about block space, usually what we refer to is the gas in a block. So if you need 10% block space, that's 10% of the available gas, which you can't use for user transactions then. That leads to like state growth and such as well. With ZKPs, we have constant costs. So you can do like a ton of computation and proving time increases with the more computation you do, but the verification stays the same. So you always pay the same amount of gas, 230K gas, for example. Now, if you start connecting chains with ZKPs, then in kind of the initial version that you do, let's say you have one chain that's connected to 3 other chains. Each of those connections is costing you 230K gas per like proof that you do, which means that, let's say 230k gas is 0.1%. That means 3 connections cost you 0.3% of the block space. And so if you go to like this 10,000 chain future, it stops working. Now, the power of ZKPs is that actually we can aggregate them. So we can take 2 ZKPs and create a third ZKP out of it. The third ZKP then again has a 230k gas cost. So really, the future that you work towards is first get to a state where we have a bunch of ZKPs being settled on chain, right? Like there's 10 being settled, and then add a ZKP aggregation layer where you now bundle them into a single one. And that then gets you down to that 0.1% again. And now that's kind of the golden standard, because that's infinite scalability that you derive at. And that's kind of proof of proof technology, but I think is like should be the future of interop. It also means at the moment of when you reach this, then you don't need to say, all right, like I'm this L2, I'm going to connect to this bigger L2 because this bigger L2 has connections to even more chains, and then I need to route through them. You suddenly get that everything is connected to everything because everyone has the same ZKP. So they all have state connections to everyone else. And so really, instead of going through bigger chains as intermediaries, you now can just do almost direct calls to everyone there. And that's kind of that step towards not really atomic composability, but really fast composability and really secure composability without there being these limbo states where, let's say you want to like route, but you need to route through osmosis. What happens if the second bridging transaction doesn't occur and now there's funds stuck on osmosis? It's like a bad state to arrive in. Really, you want that direct connection because then either the funds go back to the original user wallet or it succeeds completely on the other side. And that's the best we can do.
So basically, just to make sure that I've got the right kind of picture here, all of these chains in this diagram and any chain that Union connects to, in the block of these chains, there's an aggregation of proofs that allows them to include any, cross-chain messages or transactions that happened or, any data from other chains into their block. And then also every other chain that's connected to the Union system, or even just a broader ZK proof aggregation system, also has like validation that is like correct and is also a part of the state of their chain as well. Like, yeah.
Exactly. Yeah, exactly. Like it's basically the closest you can get to the kind of monolithic feel again, where every single smart contract lives on the same chain and they can query each other. You get that, but then for 10,000 chains all living together. So that's the final end state for interop. Like that's where we're heading to. And you can do better than that, or at least like maybe we need to smoke a joint to think about what the next iteration could be. But I can't imagine it. Like this is the end state of interop.
So like interop is trustless, permissionless interop proven by ZK technology is baked into the blocks of these chains that are just all connected by that. It's impossible to have a misalignment of state because of the ZK proofs.
Exactly. And then because you need to generate the ZK proof at some point, that's the point of like real value accrual, because with all of these like queries, messages coming in from chains, you have a big ZKP prover running. You can actually just run like snark contracts there or other circuits that do DeFi, for example. So let's say that someone from Osmosis sends a swap request or a transfer request to DYDX, and someone from DYDX to Injective and Injective to Osmosis. At this like sequencer step, you could actually prove that you don't need to do these swaps and instead do coincident of once. And so just end everyone with exactly the same end state. Or if you know what the interactions on the other protocols are going to be, it's a swap transfer that's happening, you might match that with someone else. So the security stays the same for the end user, like they get what they asked for. But you can do your own optimizations there to either spend much less gas or basically have different market participants, traders and such integrate with this.
And the ZK proofs are very easy to verify, but they're very difficult to generate. Is that?
Yeah, that's the core of ZK technology. Normally, like generating a verification, let's say that it's the same cost, but because on-chain we pay a lot for things and off-chain we barely pay anything for it. With ZKPs, what we try to do is make the off-chain cost a lot higher and the on-chain cost a lot lower. Because off-chain, we can just have a single server that generates this. And on-chain, we need to like run it over all validators to be verified. And so that's the core of ZKP scaling technology, is this kind of trying to create this imbalance for optimization.
Got it. And the reason that we can create this constant cost of ZK proofs, is that because once we're able to generate proofs at a very, very quickly and very low cost, it's very easy to verify all the ones that are packed into that one block. So the validators are doing the same thing that they've been doing, and they can easily verify that proof of proofs. But it's about packing all of those proofs, generating all of them into a single proof that is very resource intensive.
Yeah, and it's kind of amazing to see the difference, because it's quite trivial to create a circuit that could generate a proof for 10,000 ERC20 transfers, but the cost that you're paying for this is about the same cost as 10 ERC20 transfers. So really, like with ZKP tech, you get a massive scalability increase, and so in the end, like, users pay less gas, right? So more money goes to the protocol, or the whole product becomes a lot cheaper. Part of Modular, right, as well, like, no one wants to be paying 300 million in gas fees through their users to their underlying L1. They want these funds to go back into the protocol, or more trading to occur, more liquidity to happen.
100%. And that's the cost element. And then there's also the speed element that you talk about with asynchronous and synchronous composability. And so does synchronous composability get unlocked once we're able to do state verification? Because once we are able to verify the state, or I don't know if it's consensus verification or state verification, but once we're able to verify the transaction in the same proof that we're generating, that's when we're able to do these things one after another, and they don't have to run in parallel. Maybe you could kind of like demystify or unpack, like, what does asynchronous, synchronous, and parallelization mean in this composability conversation?
So it kind of depends how far you push it. For modular sovereign rollups, you can never get full synchronous composability because of their sovereignness. If they share like a sequencing layer, you can do this. Asynchronous composability, what it really means is, if my smart contract calls a DEX contract for a swap, it gets the result back immediately. Asynchronous composability means it gets it back the next block. And that's just fundamental, because like, it has to go to that other chain to be executed there. Now with bad asynchronous composability, we can get into intermediate limbo states where the swap didn't occur, but my funds aren't back either. And so there's some total failure. With good asynchronous composability, either it succeeds and everything that I wanted is executed, or I get all of my funds back. But there's no in-between state here. And that's kind of like the golden standard I think we can reach with asynchronous composability, because then at least for like the end user itself, it's kind of the same as like a Solana transfer failing. Like, you just execute it again and you try it, and not even that occurs that often, to be honest. So that's kind of the difference and where we try to push it.
Yeah, there's a few presentations so far where there are attempts at atomic composability, and very similar structure where they're trying to get a transaction to either, if you're submitting two transactions on two separate rollups, either they both go through or they both fail. And if you're able to achieve that communication across rollups, you've achieved atomic composability.
Yeah. The one downside is it's kind of similar to adding extra accounts when you do a transaction on Solana. You have to pay more for it because you need to apply more locks, right? Because it needs to succeed on both sides. So you're kind of stopping trading on the other side until this gets executed. So in like total throughput, asynchronous will beat synchronous composability because you don't need to apply these locks. So if your product works with asynchronous composability, which I think in general, like, users are used to asynchronous. Even when you interact with Ethereum or Solana, you submit a transaction and you have to wait like 10 seconds for something to occur to see the end result. So in general, most products can actually use asynchronous composability. Where really synchronous is only necessary if you want to do flash loans. Because a flash loan, you need to pay back in the same transaction. Otherwise, the protocol loses funds. So for that, you need to apply locks. I think for almost all other interactions that you do, you can actually use asynchronous.
And right now, the hardware just doesn't allow us to generate proofs quickly enough or cost effective enough to achieve synchronous composability.
That, and with synchronous composability, you lose your sovereignty because you need to now let another layer handle your sequencing. So you have a shared dependency on sequencing, which allows for potential censorship attacks again, right? Like, if you use a decentralized sequencer network where all validators are based in the US, then once again, if you do a privacy rollup, what's going to happen to you?
Yeah. So you anticipate even in, 3 to 5 years down the line when hardware is at metal and we're able to submit these proofs very cheap and very quickly, you anticipate that some rollups will choose not to share like the proof of proof aggregation to maintain sovereignty?
Well, they'll still do the proof of proof, but they will do proof of proof for asynchronous composability, because the world that we're heading to, even with decentralized sequencers right now, so they're most likely going to be 10 decentralized sequencer networks. And so you might be able to do synchronous composability within them, but then what do you do in between them, right? So asynchronous always remains like the superset, the kind of everything solution.
Mm-hmm.
And synchronous is almost an optimization within small ecosystems. You can actually do synchronous composability in Polkadot, for example. Like their protocol supports this because Polkadot itself is actually a sequencer, and the different parachains themselves are rollups, and so they use these massive sequencers for this. But you can do it when you go across different ecosystems. Like either you buy in fully into the tech and you're completely within it, or it doesn't work for you. And that's why I kind of think asynchronous will be the big driver, because it supports different products. With synchronous, you kind of get into like Polygon's aggregation layer. Like if you choose this specific tech stack and you build everything with this tech stack, it will work for you. But then we have so many people wanting to build on different stacks, right? And try to experiment around.
Yeah.
Yeah.
Really interesting stuff.
So with these groups of sequencers that tend to form around one another, we'll achieve synchronous composability within those groups, but then we'll have to have asynchronous to communicate between these different sequencer groups.
Exactly. Yeah.
For sovereignty too. That makes sense. With the synchronous, there's almost like a weakest link issue, or the most censorship, or the least censorship resistant issue.
Yeah, it's all trade-offs. You get an extra feature, but you lose on something else.
What I appreciate about the way that you think and the way that you guys are building this is you're doing this almost like with the true, like, unfuckwithable, like we're going to build stuff that can't be taken down, it can't be taken apart, that is just like almost like, almost like nation states can't touch this stuff, right? That's kind of like the end goal here.
To be honest, if you're not building your products not to be taken down by the US government, what are you even doing, right?
Oh, bro, I love it. All right, so kind of going back now to like the practical, well, the ZK stuff is quite practical, but like the more of like, okay, what can our community watching this understand as to how this like looks? So yeah, I mean, we've talked a ton about this, but maybe just like explain a bit about this diagram, like what's happening here, and is it any different than what we've just talked about, or maybe explain a little bit here as to what's kind of going on.
Yeah, so the initial state that we're working towards is not yet the full proof of proofs. So for certain chains, we might settle multiple ZKPs. That's very much like a value decision on our side, because on some chains, gas is cheap enough to just do a few for multiple connections. Initially, Union was very much Cosmos focused, but in the meantime, we realized that actually kind of it's like network that can be taken down by the nation states is wanted by almost everyone out there. So we've branched out first into the Celestia ecosystem. Now we're in talks with Avail. We actually like some alpha. We have our scroll integration almost ready. So I think our principal engineer was tweeting about that stuff. And so we're really like broaching out to the interop layer that crosses everything that's happening. We're at ETH Denver now, and we have a bounty out as well. So the first kind of developers that aren't even from companies that we partner with are starting to build on our stuff. We're doing a ton of work right now on docs and UI rollouts. So expect that in the next couple of weeks. And that kind of allows people to start playing around with this stuff. Some things I'm extremely bullish about, even though they're kind of on the smaller side, is, for example, the first Stargaze integration, which allows us to have Stargaze settle on Ethereum and kind of make that an NFT co-processor for Ethereum, which is nice because at least like I own some bad kits. So I'm happy to support that ecosystem. And on a wider scale, with a lot of the new tech that's being built on the Celestia side, like movement and such, basically this means that we get like enshrined interoperability. So for third-party devs building on top of this, you can just interact with other products out there. Like you can just access liquidity without paying high fees, without needing support from a specific intro protocol out there. In the end, like it's still interop, so it's still bridging transfers, message passing, interchain accounts, and storage proofs, so data requests. But At least I think that's it's the only solution I choose as a developer out there right now. Compared to all other bridging solutions, it has the least friction and the best capabilities.
And right now you've got at least 2 proofs that are going on here. You've got the DA proof from Celestia and now Avail. And then you've also got the settlement proof to Ethereum.
Yeah. So for example, like this diagram isn't like completely correct. It's a nice overview. But what we're doing for movement, for example, is we're generating one ZKP, but it tracks movement consensus and Celestia's consensus. And so we fold both of them. So it's kind of 2 live clients in one single proof. It already shows the power, because normally you'd need to track both individually and pay for both individually, but now you get them at once. For Scroll, we are running live clients on Scroll itself. So those are folded into their proofs. Scroll settles about every 30 seconds to 1 minute on Ethereum. The Scroll live client is actually an Ethereum live client. And we access Scroll's data through a storage proof. And so when you want to connect to Scroll, you automatically get a connection to Ethereum as well with that. Or the other way around, if you connect to Ethereum, you are connected to Scroll. And there you already kind of see this like scalability starting to roll. And we'll see the same with Polygon and their aggregation layer. Like you kind of pay to connect to once and you get all of them for free.
There was a term that you mentioned on a live stream that we did around interoperability a few weeks ago. And you didn't touch on it here, but I was hoping to hear a little bit more about it, which was single slot finality. And I think from the sound of it is very important for synchronous composability. So I'm curious, like, how does single slot finality fit into this proof aggregation and like the life cycle of one of these proofs?
Yeah, so single slot finality means that the moment a block is produced, it's immediately finalized. It's never going to be reorged again. Cosmos chains do this, but some other chains don't. Ethereum doesn't do this, for example, which means that Ethereum actually very often has 1 or 2 block reorgs. You need to wait for that. Like you can't execute the bridging transfer, because if a reorg occurs, then the deposit sides might just disappear from the chain entirely. So on Ethereum's roadmap is single slot finality as well, which means that the moment you kind of get your transaction submitted in the block, it's never going to disappear again. So it's great for end users, great for bridging protocols. It's basically the same as a rollup that settles very, very often. And you can kind of compare not single slot finality to a rollup that has like a 1-day fraud proof window or something. For full security, you technically need to wait until you like reach finality or until like the dispute window is closed if you want to be really proper with how you do stuff. In my opinion, like every chain should have single slot finality. Like it's a no-brainer. Most chains that don't have it right now really don't have it because they just didn't implement it initially and it's on their roadmap. It's a bit harder to do on the Ethereum side because they obviously have an existing system. They're not building from scratch. But it's actually looking really good. Initially, their assumptions with kind of how the new consensus works with BLS signatures and such, they thought it would be more work on the nodes, but from like the actual metrics from mainnet right now, it's not at all. So the roadmap for single slot finality is looking very good because the current system actually scales very nicely. To us, like on the Ethereum side, we need to wait a couple of blocks. You just can't have this reorg occur. As bridging providers, like if you have this off-chain architecture, you can choose to take a risk if you want to. But it's always risky because the protocol can just lose money. If a validator produces 2 blocks and submits 1 block to the network, 1 block to the oracle, then it can use that to do what's effectively a double spend attack.
Yeah, and we've seen, I mean, on some deposits and withdrawals, you've seen, waiting for 100 confirmations or 50 confirmations. And that's to make sure that the blockchain doesn't reorg. Because if you only waited for 1 confirmation, it might reorg, you might lose funds if that blockchain doesn't have single slot finality. But I think what you're getting at here is that if you do have single slot finality, you can proceed with the rest of your transaction after a single confirmation.
Yeah, exactly. The moment it's produced, it's confirmed. So it's a no-brainer, like every chain should adopt it.
Yeah. It's pretty awesome. That ties in here well as well, right? Like this system that's on the screen it becomes even more powerful when single slot finality is more adopted.
Exactly. Like the future is single slot finality. It's ZKPs, and this isn't just for interop, right? Like all of these things just make sense for user transactions in the end. Like it doesn't make sense that if I like input data with my bank, it does work. And if I do it on some chains, I need to check back in 10 minutes to verify if it's actually arrived or not. So for Web3 to actually be adopted, we need SSO.
How do you handle latency in a proof of proofs landscape? Like if one rollup submits a transaction every 10 seconds and another rollup submits not a transaction, but a block. One rollup submits a block every 10 seconds, another rollup submits a block every 30 seconds. How do you reconcile the 20-second difference between the block times?
Yeah, that's not really a problem. You can make a choice. You can basically decide to produce a proof in a certain interval, and everyone that gets in during that time and is lucky. You can also generate a proof the moment new data gets in. You don't necessarily need to settle it, but you could if you wanted to. And then you just build on continuously on that proof until it makes sense to settle. So with these systems, what you ideally do is you continuously generate the proofs, and you kind of keep a tally of how many fees have accrued. And at some point, you can then say, all right, like there's enough right now to warrant the cost. So the more change you have connected to this, the more often you're going to be setting this across. With the proof of proof technology, and if you build continuously on these proofs, you also don't necessarily need to provide it to everyone at the same time. Even if all of them have data coming in, if like only transfers are heading into ZK Sync, for example, you only need to settle the next ZK proof on ZK Sync, and then you just generate another proof where perhaps now transfers are coming out from ZK Sync, you build on top of that, and then you settle that back to the other parties. So you can actually do like really clever optimizations here to even cut the costs down more.
Yeah. Well, Karel, I appreciate you coming on and generally just blowing our minds for Modular March. Really excited to see some of this stuff come to light. And yeah, man, stoked for the future of ZK. I think that ZK has a lot to offer, and we're just at the cutting edge now.
Same, guys. Thanks for having me. Super excited to be on again in a couple of months and show you guys all the progress.
Awesome. Looking forward to it.